Hello students, we will see now the frequency response analysis of the control system. The frequency response analysis of control system is nothing but the steady state response of the system to the sinusoidal input. The frequency response analysis is carried out in frequency domain rather than in time domain. Normally, the time domain properties of a control system can be predicted from the frequency domain characteristics, and we will see this in the later lectures. For an LTI system, the Laplace transform of the input and output are related to each other by the transfer function Ts. It means that if Rs is the input and Cs is the output, then the transfer function Ts in time domain is equal to Cs upon Rs. In frequency response analysis, the system is excited by the sinusoidal input of fixed amplitude and varying frequency. Let us subject a stable LTI system to a sinusoidal input of amplitude R and a frequency omega in time domain. So, RT is equal to capital R into sine of omega t. The steady state output of the system will be again a sinusoidal signal only, which is having the same frequency but magnitude or different amplitude and phase. So the output Ct is equal to capital C into sine of omega t plus phi, where capital C is the magnitude of the output and phi is the phase angle. We can see the phase and gain relationship as shown in figure. There is a phase difference in between input and output. Similarly, the magnitude of the output and the magnitude of the input is also different. To carry out the same process in the frequency domain for sinusoidal steady state analysis, one can replace the Laplace variable s with s is equal to j omega in the output and input relations. So, in time domain, as we can write, Cs is equal to Ts into Rs, which can result C of j omega is equal to T of j omega into R of j omega. The input, output, and the transfer function have now become the complex, and then this can be represented by their magnitude and phases. So the input R of j omega is equal to magnitude of R j omega into phase of R j omega. While similarly for the output C of j omega is equal to magnitude of C j omega into angle of C j omega. The transfer function T j omega is equal to magnitude of T j omega into angle of T j omega. With similar expression for the input and the transfer function, the input-output relation in the frequency domain consists of magnitude and phase expression. That is, normally we write C of j omega is equal to T of j omega into R of j omega. So, the magnitude of output, that is C j omega, is equal to magnitude of T j omega into magnitude of R j omega, and the phase of C j omega is equal to phase angle of transfer function plus phase angle of input function R j omega. For the input and output described by RT is equal to capital R into sine of omega t, and the output Ct is equal to capital C into sine of omega t plus phi. The amplitude and the phase of the output now can be written as the amplitude of the output capital C is equal to amplitude of input R into amplitude of transfer function, while the phase angle phi is nothing but the phase angle of the transfer function. Consider the transfer function for the general closed loop system. That is, in time domain, we can write Ts is equal to Cs upon Rs, which is equal to Gs upon 1 plus GSHS. In frequency domain, the same steady state behavior can be written as T of j omega is equal to C of j omega divided by R of j omega, which is equal to G of j omega divided by 1 plus G of j omega into H of j omega. So, T of j omega is called the frequency response function or sinusoidal transfer function. The frequency response function can be written in terms of magnitude and phase. So, the transfer function Tj omega is equal to magnitude of Tj omega into phase angle of Tj omega. Since this function is a complex, it can also be written in terms of real and imaginary parts. So, the Tj omega is equal to real part of Tj omega plus j into imaginary part of Tj omega. Remember that for any complex number, it can be represented in the real and imaginary parts. That is, z is equal to a plus jb. The magnitude of this complex number can be written as the magnitude of z is equal to under root a square plus b square. And the phase is given by the angle of z is equal to tan inverse of imaginary part upon real part, that is equal to tan inverse of b upon a. The magnitude and the phase of the frequency response function are given by magnitude of Tj omega is equal to magnitude of Gj omega divided by magnitude of 1 plus Gj omega into h of j omega. And the phase of Tj omega is equal to phase of Gj omega minus phase of 1 plus Gj omega into h of j omega. These are called the gain and the phase characteristics or the magnitude and the phase relationship. So thus we can carry out the frequency response analysis of any control system, and further this can be carried out with the help of polar plot, Nyquist plot as well as Bode plot. So thank you.